Welcome, everybody, to the launch of Houdini 18. My name is Chris Hebert. I'm the Director of Marketing at Side Effects. 2019, it's been another amazing year. Over the last few years, we've had huge growth. And on our side, that's from an ever-improving product. It's from increased awareness, adoption, learning material, a strong focus on schools where we've had amazing growth all over the world. But really, the growth is thanks to you, the community, the heroes in the studios and the schools, the freelancers around the world, helping people learn, helping spread the word on Houdini, whether it's creating tutorials, delivering presentations, creating courses in the schools, crafting tools, or just leaning over somebody's shoulder and giving them a quick tip on how to use a node. Kudos, huge kudos to you guys, and we just thank you for helping us deliver this product to the world and use it and create such amazing work with it. So to support this growth, we've invested. We've invested in the team at Side Effects. We've almost doubled over the last few years in size in departments all across the company. We've invested in our partnerships with technologies, the integrations with technologies across the pipeline. We've invested in learning material for both new users and experienced users because, as we all know, we're all learning all the time, and especially with Houdini. So with Houdini 18, there'll be a new batch of learning material, some of which will come out on day one, and some of which will roll out over the next few months. So keep an eye on sideeffects.com/learn. And last, but absolutely not least, we've invested in the product. And here to tell us about all the new additions are VP of R&D, Kristen Bargil, and Senior Product Designer, Scott Keating.
Good evening, everyone. I'm Kristen, and this is Scott. Welcome to the launch of Houdini 18. Which is another major release in more ways than one, once again. We're particularly proud of the project Solaris, which stands to become a game changer for lighting professionals, but also for full-on pipeline development. Also with Project Solaris and beyond, we've taken some pretty bold design decisions with how we give you access to the physics in Houdini. And also beyond that, we've taken our physics solvers to the next level. In fact, we've looked at the whole landscape of solvers in Houdini for this release, and we've touched all of that. And we sank our teeth really deeply into interactive modeling and also computational geometry in this release. So just to give you an idea, we've touched or created about 200 SOPs in this release, and we're just getting going. All right, so let's start with Solaris. I'll do just a quick intro and then pass it on to Scott. So this is a unified USD-based environment for lighting and layout and rendering and lookdev. And what's really key about this is the USD part. So that's Pixar's Universal Scene Description, which runs through the veins of the Solaris graph, which is called LOPS, by the way, in other contexts, as real data. This is a native USD implementation. It is with USD at the core. There's no import into some proprietary API and then export. You have USD throughout, and that gives you a lot. First of all, it gives you full access to USD. It's very faithful Solaris in the way it gives you access to all the USD componentry and functionality. Nothing gets lost in translation because there it is, it's USD. And then thirdly, equally importantly, anyone and any software that is fluent in USD and Hydra, which is the other API that goes hand in hand with USD, so any software like that will automatically plug into Solaris easily. And through our experience with third-party renderers, we can tell you that that's been the case, and it's a joy to see that. All right, so if you can press next, please. So the pipeline aspect of that is interesting because when we set out to do this, we were thinking, all right, we want a cohesive, brand new system for lighting. And one that, of course, opens up to many renderers, but it's for lighting and rendering and whatnot. And then we discovered by going through USD, the people that got most excited first were pipeline people. And that's what we've been seeing now for the couple of years that we've been developing this, and you'll hear it from someone in the audience later tonight. It's the pipeline people that I found it immediately useful and very robust in addressing exactly their needs. So yeah, we think that Solaris is a seminal piece of architecture in Houdini, not just because it embodies our vision for a unified system for lighting and rendering, but also because it exposes USD in all its entirety, with nothing held back, with nothing tainted. And also, it gives it to you, it offers to you in a way that's easy to consume and understand. Someone said a few months ago, Solaris gets it, and we hope that you guys do too. So next is something called Karma. So as we're writing this environment for lighting, we couldn't continue with Mantra. Mantra had an architecture that belonged, you know, in another environment, not in something that's USD-native. So we decided to set Mantra aside and write a new renderer. This is what Karma is. Karma is USD fluent, Hydra fluent, and it is excellent, thanks to Hydra, at doing IPR, which is something that Mantra always struggled with. But I want to clarify right off the bat that Karma is not just a preview renderer. Karma is the future replacement of Mantra. It is a full production render. It is currently a CPU engine, but we have every intention, in fact, we've started, but very early stages, we've started to look at the GPU architecture for it as well. Karma is a fresh little kid, hence the beta stamp in Houdini 18, but nevertheless, I think it's a lot of fun, and you'll see it a lot in Scott's slides. And with that, Scott, take it away.
I'm going to walk you through all the new features of Houdini 18, and we're going to start out with Solaris, because it's sort of new and exciting, and I'm very happy to share it with you. So the first thing I want to mention is that earlier this year we did a sort of a reveal of Solaris where we talked a lot about USD and pipelines and how everything works together as this technology. That's all really, really important. But a question a lot of people had was, well, what if I've already done setups in Houdini? I have object-level objects, I have materials. What about me? Like, how do I transition into this new world? And so we've put a lot of effort into taking a scene like this, an object-level scene, and easing that transition by creating nodes that will import as much of that data as possible into Solaris. So you can see with this single node, this scene import, we're pulling in all the materials, textures, geometry. We're converting instances into native USD instances. And so we're trying to make that as smooth as possible. USD has its own features, its own ways of working. So sometimes there's some data loss between here, but we've created a whole suite of tools to make it as easy as possible to get things into Solaris and immediately start taking advantage of Karma and rendering in this new environment. So also when we talked about Solaris before, we did a lot of focus on the underlying technology because it's very powerful. There's a lot of really interesting things you can do with USD, and that's sort of brought to the forefront with this node-based approach. But today we want to focus a little bit on like the actual workflows, like what you're going to do day to day using Solaris, say, sort of as an artist doing lighting. So let's start with layout. So layout, essentially bringing a bunch of stuff together that you're eventually going to render. There's lots of ways to approach it. We're just going to show you a couple of interesting things here. So first of all, let's talk about set dressing, essentially. So we've got this carousel scene. On the right side of this node network, you can see a bunch of imports. And essentially, we're just bringing in some geometry for leaves, things that we want to instance into our scene. So inside this instance to points nodes is a geometry network. It's a SOP network. And that's really interesting because it means that you have basically all of the procedural geometry and attribute editing tools that we have access to in the rest of Houdini inside of Solaris, inside of LOPS. So here we're just doing some pretty standard Houdini sort of editing of geometry. We're going to use this group to isolate sort of the faces that are facing upward, more or less, because we're going to add some debris to our scene. And so something that's really nice here is that we can use these standard tools, but we can see into Solaris through the barrier between SOPs and LOPs. So much like you can ghost geometry in the background at object level, you can essentially show Solaris through your SOP network. So even though I'm painting on SOP geometry here, we're actually viewing the result in Solaris. So you can see I can very quickly paint my leaves on here using standard tools, jump back up to our Solaris level. The instances have been placed properly into the USD hierarchy, so they follow all the transforms of the carousel. And we can immediately jump into Karma and check out the results of our quick little layout here. And so you can see if you're an artist and you're working with tools like this, you have a very simple network, but you still have access to a very wide range of very powerful geometry editing tools. But what about when you have a more complex asset? Obviously, a leaf, it's basically a couple of quads. It's nothing that complicated. So let's look at a tree here. So one of the really nice things that USD offers you is the fact that an asset is more than just an asset. Typically you might think of an asset as like geometry, maybe some texture maps, maybe a material. But we're going to take a look at a different approach to an asset. So first of all, we've built this little quick tree tool here. This is just a little tool we whipped up for this demo so we can quickly create a bunch of trees. Again, it's nice to have these geometry tools available to you inside this essentially lighting package. And basically, we're creating a high-res version. I think it's got something like 24,000 polygons or something, and a low-res version of it. So USD has this concept of a purpose, and there's a bunch of kinds, but we're looking at render purposes and proxy purposes. And what this basically allows you to do is, in your asset, define when you should use certain types of elements in your setup. So basically on the right, we're importing our low-res proxy geometry, and on the left, we're importing our high-res, final render geometry. And we're just using this node called configure primitive to say, my purpose is to be a renderable object, something at render time, and the low-res is basically for OpenGL. And what that means is that as soon as I have set up this basic setup here, the artist no longer needs to concern themselves with it. I can just look in the OpenGL viewport and see the low-res proxy, and when I switch to Karma for rendering, we immediately get the high-res version of it. And this is built into the asset. And so what that means is that the only thing you need to think about is, was the asset created correctly? If it was, the artist who's using it, it's transparent to them. When they switch to the different views, they get the correct model to use. So now that we have this asset, let's do something interesting with it. So we've imported 4 different trees here, just using a reference node. These could be set up as variants, but for simplicity's sake, we're just going to bring them in separately. And we're going to use a same node that we use with the leaves, this add point instancer. We're going to plug in a grid just so we have a sort of a ground plane for our instances to live on. And you can see that by default, we can just target anything in that second input. We're just using a wildcard there. And then the random seed value lets us see our different variations of trees. So okay, we've got our grid, we've got our ground plane. We want to make this a bit larger, just so we've got a bit more room to work with. And we'll throw down a light here as well, just so that we can see what our full tree looks like. Again, nice having this active IPR there so you get the clear rendering results as you're working. But basically, we're just going to go ahead now, go back to OpenGL, dive inside our point instancer, and start adding some nodes. So we're going to start out with just some grids, and you can see a tree showing up at each point on the grid. We're going to just merge those together. And then again, we've built another little quick asset here to add some attributes onto those points. And you can see right away we get now random versions of our trees instance onto those points. And because we've taken the time to set up these render proxies, everything stays very fast, very interactive. You can see a large portion of your scene and still work with the tool interactively. So you can see that I can still drag these handles around and have the instances update. And of course, back up in Solaris, we can go immediately to Karma and start rendering the instances. And I forget exactly how many. I think there's like 15,000 trees or something like that. But the point is you can get the result pretty quickly. We try to keep in the top right corner the timing visible there so that when we do speed up the view so that you're not waiting around for things to happen, you could get an idea of how long something is taking to render. Okay, let's go back inside. And here's where things get really interesting because, again, because we have these access to this huge suite of tools that exist for modifying geometry, modifying attributes, we can take advantage of those things for render time effects. So here we're just throwing down an attribute noise node. We're just going to generate some noise on our points. We're going to use a color node to sort of remap that noise into sort of fall-ish colors. And then we're going to drive the shader on our tree assets using this data. So you could do things like this previously in Houdini using style sheets and so on, but it was quite complicated. Here it's very straightforward. On the point attributes to copy, we set the leaf intensity. There is an input to the shader with the same name. We automatically copy those render vars into the correct spot in the shader, and we can get this nice fall-looking forest pretty quickly. So it's really nice to have this ability to, not just drive the placement and positioning of things, but to override elements of the assets using these point attributes. And we've gone through quite a bit of effort to make sure that when we copy attributes from points onto things like instances or references, that we convert them into the correct thing, whether they're properties or render vars. So here's a more complicated example. This is a very large sort of city scene, several times as big as the center of London, as I understand it. So it's quite large. And there's literally going to be billions of polygons here when we're done. So we just want to show you how capable our viewport is of handling production scale scenes. And here we're just doing a very simple import of different layers. So the sort of roads and streets, the buildings, which are basically made up of nested instanced assets, trees, props, and so on. And you can see we can bring in all that detail. The viewport does cull data as it comes in to keep things nice and interactive, but you can see we have a massive scene. And having a massive scene like that is really nice because you can actually look around and choose things. You can frame your camera with geometry without waiting for a rendering to occur if you don't want to. But it also means that you can continue to work. So in this example, we're going to do something, it's a little bit cooking show style where we're going to select some buildings here that we want to destroy. These are all instances, as I said. And we're going to use a node called extract instances. And we're going to take that now from basically a huge point cloud and turn it into real geometry. And then we're going to kind of skip ahead because really this is standard sort of Houdini destruction stuff. We're going to talk about that a little bit later. But we're going to use these nodes called SOP import to pull that data back in to replace those instances. And you can see now we've brought in our destroyed buildings just using a couple of these SOP imports. And this is happening on its own layer. You can see that by the coloring around each node. There's these green layers and then these blue layers. And what that means is that, again, somebody doing layout, somebody creating assets up front can work at the same time of whoever is doing the effects. They can pull the effects out, work on it at the same time, and using this layering system, place it back into the appropriate place without interfering with the other person's layer. That's really one of the most powerful concepts in USD. And here you can see the playback now showing the buildings being destroyed, and it looks pretty cool. So on a much smaller scale, sometimes you just need to place objects in your scene. So we've created an edit lop, and it has this idea of physically based editing. So what's happening here is that we're running a simulation sort of under the hood. So as I move these objects, they interact with each other, they push each other around, they have collision geometry associated with them, and so we're using something called a relationship in USD to define collision geometry and render geometry, very similar to the concept of the low-res tree and the high-res tree. But what it lets you do is very quickly place objects in your scene in ways that aren't easy to do using standard transform handles. You can get very natural looks. You can grab any part of the object and pull it, and it will sort of behave naturally. Creating these sort of stacks and piles of things becomes very fast. And if you see a little stuttering there, I just want to point out that that is not a frame rate issue. That's using the scroll wheel on my mouse to add gravity to the scene. So every click adds a small amount of gravity, letting things sort of settle into place. And things like these barrels, it becomes very natural. Just tip it over, roll it up against the other barrel. Like, again, a layout artist can absolutely do this manually without too much trouble, but being able to do this in this like semi-natural way gives you sort of abilities that would be difficult to do. It would require a lot more planning to get it to work. Whereas here I can simply grab these brooms, push them to the other side, and we get a nice sort of pile of objects here. Or even just leaning a broom against a table like this. In a normal circumstance, you would need to move the pivot to the corner of the table and so on. So again, just taking standard sort of tools that an artist is used to and bridging them together with our sort of traditional powerful simulation technology to create an overall workflow like this that just wasn't really possible to do before. So obviously, we talk about Solaris as a lighting package. And what that means is that obviously a lot of the time you're going to be lighting things. You're going to be moving lights around. So we wanted to make that as sort of as smooth as experience as possible. And the first way we've done that is obviously the IPR view helps, the fact that Karma is rendering nonstop. But we also made some changes to our handles to make things easier. There are indirect drags for changing the intensity of lights, for instance, so that you're not always having to go to the parameter pane to make these changes. There's a look at handle, so you can snap your look at to an object. These are all sort of very expected things for handles to be able to do, but we've made some updates to make them work a little nicer, a little smoother. And of course, we have this look at handle on the other end as well, so that if you are zoomed in on the horse, for instance, you still have access to the light. And this is sort of the base level. We want to make sure these things work, they work well. You can change the size and intensity of lights in a nice interactive way. But we wanted to take that further. So what we've done is we've created these different states for different types of lighting. So here I can just click on the surface of an object and we'll align the light to the surface. And that way, if I want to light the front of the nose, for instance, I can just click there. And this is an interesting tool just on its face, but where it becomes really interesting is it means that a lighter can work from the camera's perspective, right? They don't have to be in a different perspective moving these lights around. We also have handles to move the lights further away or toward the object. But also we can do that while maintaining the intensity. So you can see that the spot on the horse actually stays the same brightness as we move the light further away. And again, that means reducing the amount of sort of tweaking that an artist has to do. If they have a light that they like and they like the intensity, but they need to tweak the position a small amount, it's very frustrating to move it and then go, oh no, I need to change the intensity now to match where it was before. And of course, we can also bring up that same look at handle in this mode if you do want to do some fine tweaking of the position. So then we have something that we're calling a shadow target mode. And essentially what this is like a light pivot. So I can click on the head of the horse and then click anywhere else in the scene, and we're basically going to project the shadow onto that point in the scene. So you can see I can just drag around and basically place that shadow exactly where I want it by creating a pivot on the horse's head where that the light moves around. And this becomes, again, a way of working to get a result as a very standard thing to want to be able to do. But to get it while looking through the camera's point of view. And so suddenly the task of a lighter is much more interesting. There's less jumping around. It's more about art directing the scene, sort of painting with light, as they say. And then there's specular. So here we have a tool for placing specular highlights. So rather than lighting the surface diffusely, from my camera's perspective, I can say I want a reflection of a light at a specific part of my object. So when I click on the saddle, you'll see that we don't move the light there, we move the reflection of the light there. And so as I drag over the surface, I can create glints and highlights exactly where I want them, again, from the perspective I'm working at. And this is really useful when you want to create sort of rim lights and so on, but also especially in the idea of a character where often somebody says, oh, I need a light, in the eye of this character. So here you just simply click on the surface and we'll move the reflection there. So again, trying to take all the common tasks a lighter would do and create these streamlined workflows to make them more entertaining to actually do. It's fun to use these tools, but also more practical. And then there's depth of field, which is really more of a camera than a lighting issue. But a big problem with depth of field is that you have to say where that focal plane is. So if we enable depth of field here, you can see this horse in the background has the focal plane basically on its eye. So we can enter focus mode, and now anywhere I click on the surface will actually draw that focal plane. So you can see exactly where your focal plane is cutting through your geometry and immediately update the focal plane to that point. And so this is really important. Again, it allows you to sort of move through your scene in a more interactive way from the camera's point of view without sort of, again, messing around with a lot of camera properties. Things become very immediate. It's like focus pulling rather than placing handles in your scene. So let's look at a practical example here. So we've got these bottles, and we want to very quickly light this scene. So I'm just going to go into my network, drop what we're calling a key light. You can see, especially with objects like this, how useful it is to be able to do that specular placement, because a lot of these shiny surfaces get their surface properties from the reflections more so than the direct light. But we can just quickly put down some lights to reflect on these bottles on the right side, and go ahead and place one on the left side. I'm not worrying too much about the intensity of these lights at this point. I'm kind of just getting them down, sculpting the scene with my lights. I'm going to go ahead and add a top rim light to cut out the top of this object from the background. And now we'll put down an actual spotlight. So we've also changed our spotlight handle. So if we just pull back a bit, you can see I can just click where I want the spotlight to point, and we have a new spotlight handle that lets us change, again, the intensity indirectly, but also just grab that spotlight and pull it in to change the position of the spotlight. And of course, we have parameters that are new for our lights for things like barn doors, so that you can sort of sculpt the light even further, change that shape dramatically, bring it down, so we're sort of cutting our image in half there. And then we have this dome light or an environment light. And in this case, we just want the reflection. So we can just simply turn down the diffuse multiplier, remove the diffuse contribution, and just stick with the reflections. And so you can see in just a couple of minutes and just a handful of nodes, you can very quickly lay out a scene like this. Now, obviously, you want to tweak the intensities of these lights, but as a first step, a pretty fast, pretty painless workflow. So the next thing is to start doing what's called light linking. And light linking is basically saying things like, I want my key light to only light things that are on the table. And you can do that very simply with this new interface where we have these different scenes. So for instance, bring in all of my rim lights, but that's a little tedious. I've got a bunch of lights. So we can create something called a collection instead. And I can just call this all rim lights. And now we can create rules for all of those things simultaneously. So I bring in my rim lights and say only the bottles are lit by the rim lights. And now you can see how we're changing our overall view here. Then we can also do shadow linking. So you can see I brought in this table lamp, and I'm saying remove the shadows from the bottle from that light. And we don't actually want to do that in this case because it doesn't really make a lot of sense, but it's possible. And then you can go the opposite way. So in this case, we brought the geometry in and said this geometry is only lit by this light. So you can actually work on either side, light-centric rules or geometry-centric rules. And the really nice thing is that these rules then persist. These are USD rules. They're on the lights themselves. They exist essentially as collections. So if I add a new light to my scene, and then I go downstream and I add a new light linker, you can see that all the previous rules are still there, right? They all show up. They can be read. And so this doesn't just come from the network upstream. It comes from the USD itself. So if you just brought in a file that had these rules, they would show up here in the light linker. So you're never less sort of guessing like, oh, did somebody else in some other scene set up these rules or not? They're all here for you to be investigated directly. You can see they're sort of tinted a dark gray like that to let you know that they've been imported. They weren't created in this node. Now, finally, we want to start talking about the actual color and intensity of these lights. So we're going to use the same group that we used before, except now in this thing called the light mixer. And these are sort of custom UIs designed to give you this high-level view of what's happening in your scene. By the way, these are all Qt widgets, which means that they're quite customizable if you wanted to change some of the behavior here. But basically, the idea is that I want to now sort of go light by light and start tweaking things in my scene. I can easily solo the lights by clicking the solo button. Obviously, I can tweak the colors and so on. And because we've already set up our light linking, everything sort of behaves the way we would expect. And then these light groups are really interesting because you still have access to all the lights inside the group. So I can individually tweak, for instance, the right rim light, maybe make it sort of a cooler color. I can tweak the left rim light and so on. But I can also say, no, I want to do the entire group all at once. So I can control every light in there. I can even tint the lights inside that group. So if I want to move them all slightly more green to help them tie in with the background a little more, I can do that. So we still keep the overall intensities. We're basically adding a tint on top. So you have a lot of control over how you interact with these lights. Here now we're just adjusting the sort of little kicker that we added to the label. But of course, what if you have like a lot of lights, maybe 100 lights? It's entirely possible that you would. So there's also this sheet view that gives you even more information than the mixer does, but still lets you do things like mute lights, solo lights, change intensities, and so on. So this is more of a low-level view of your scene where you can get a quick overview of many, many lights. That wouldn't just be practical to do in the light mixer itself. So what about procedurally doing this? Part of Houdini's benefit is that we have these procedural networks. Here we have a little network that takes a bit of text and it extrudes it, bevels it, puts a profile on it, adds this sort of interesting outline around the outside. So can we take advantage of that to do lighting tasks? And absolutely we can. That's part of the beauty of this whole ecosystem that we've created, is that I can dive into this network and start pulling geometry from wherever I like. So in this case, we're going to grab the sort of wires that define the outlines of our text, and we'll just resample those so that we don't end up with like a million lights. And basically what we're going to do is, again, just sort of standard Houdini stuff. We're going to manipulate this geometry in order to create light copies on all those points. And you can see already it's working. If I move this out now, you can see the little spheres that have been copied to each point in our geometry. And that's lights. Those are lights that will eventually drive our scene. But let's take this a little bit further. So similar to how we override parameters on the shaders of our trees, we can do the same thing with properties on lights. So here I'm going to create something called an offset. And really this is just manipulating some underlying rules here to create sort of an interesting fall off for our lights. So I'm going to take that ramp and I'm going to create this interesting sort of effect where we move the lights around like sort of an old style billboard. Then we're going to ramp those colors so something a bit more believable. Black and white is probably not the type of lights you would be using. And all of this information that we're creating here, all these attributes, they can be used to directly override properties on lights, like the intensity of the lights, the color of the lights, and just like our tree example, basically all I need to do is let the instancer know which attributes to copy. So in this case, it's color and intensity. And you can see immediately we get this result in the viewport. So this would be very tedious to set up by hand, especially if changes are coming from upstream. Especially when you start making it even more complex. So we've started with just the lights, and now we want to create some geometry that represents, the light bulb. And we can basically literally just copy the entire network that we just made. You could even reference it in if you wanted to, but in this example, it was simpler to just copy it in. And really, we just need to change the names of the attributes to match properties on the shader of the light geometry. So now when we come back up to Solaris, to our /stage context, and change the attributes to copy, things sort of show up nicely, but you can see the geometry is blocking the lights because the lights are essentially inside those little spheres. But again, we can just use that shadow linking that we created before using a procedural collection. So in this case, a rule-based collection that says anything called light, go ahead and put it in this collection. Or in this case, instance. You'll see it shows up here in the light linker. It has all the lights inside of it. I just drag over a shadow rule, bring in our geometry, and suddenly it doesn't cast shadows anymore, and we have this nice effect of a shader whose color values match the light that it's meant to represent. So tying those things together. And then, of course, because this is in a Houdini network, we can, of course, go back to our original thing, change the title on all the lights, everything updates. And so now, what was once sort of a static setup becomes basically alive. You can adjust things. You can change values over time. And Solaris really becomes a procedural layer on top of USD. USD, generally speaking, is describing static things. But these networks allow you to inject this layer of dynamism, of action on top of the USD. And here now just a full render of this sequence so you can see how it works and how annoying it would be to set that up by hand. And of course, this basic technique can then be taken even further to a more practical scene. So here we have the carousel with thousands of lights on it, all being driven by essentially the same type of network, rendering, in kind of the worst possible scenario for a renderer with thousands of very small lights near very reflective objects. But you set it up, you can tweak these things, and you get these really nice results, along with motion blur and all of the great stuff that a full render gives you. And just because it was interesting, we also did an OpenGL flipbook of the same scene. So this is OpenGL with the quality settings basically turned all the way up. We're sampling sort of buckets of 30 lights at a time, but still with a maximum, I think, 2,000 lights. And you can see remarkably high quality, given the fact that it's just a real-time renderer. So we talked a lot about assets and things that you would do with Solaris. But if you're going to be creating all these assets, you're going to be creating all of this stuff, it would be nice to automate some of these processes, right? A lot of it is something that is absolutely automatable. So let's take a look at a PDG example here where we're going to use Shotgun as sort of a library of assets. So here we've got Shotgun. This is where we want to go. We want to be able to have assets that exist here in this asset browser. They've got turntables associated with them, thumbnails, everything you would kind of expect. But where we're starting is basically a list of assets with none of that stuff attached to it. So how do we get from here to where we want to go? And the answer is a network like this. This is a pretty straightforward PDG network. Something interesting to look, if you're familiar with PDG, at the very top of the screen, you'll see this new bar that we've added to the UI that lets you track the overall work that's occurring. It also has some nice buttons and things if you want to start or cancel jobs. But essentially what we're doing is in the first block, we're getting asset information from Shotgun. In the second block, we're processing them. And in the third block, we're re-uploading them to Shotgun. So let's just quickly walk through this process here. So first of all, this is something called a command chain. And basically, we're just sending commands to Shotgun to say, look at this specific project, give me all of the assets that are there available, and hand off that data to me in a useful way. So if we actually go ahead and investigate one of these work items, A, you can see how the asset has traveled through the network, but B, we can inspect it and see like, oh, we have this barrel asset. It's a USD file. It's up there. It's ready to be processed. So from there, we want to move on to actually processing these assets. And here's where you might do basically anything you can do in Houdini, but in this case, we've actually attached it to a Solaris or a LOP network. So you can see we have this LOP network called Turntable Assembler. And if you look at the connections, by the way, you can see we're still tracking that same barrel asset. And basically, this is the LOP network. You'll notice it looks a lot like our tree asset that we created earlier. Except in this case, we're assigning materials, we're loading in a layer that represents the turntable, and in this case, it's an interactive, so we're looking at the actual result live here, but of course, the goal is that this is offline. It happens automatically. But it's nice that PDG lets you examine the networks live like this and verify the results. So from there, we now go into our render USD scene section where we're basically generating all of the data from that LOP network. And then we're going in to assemble those into useful things. So on the right, we're creating film strips, thumbnails, on the left, and on the right, we're generating actual videos from the turntables. And once again, if we examine that work item, you can see all the data that's on there, and we can actually click and open up the associated video, again, just to verify that it successfully generated the thumbnail, or the turntable in this case. And then from there, we're basically kind of doing the opposite of what we did in the beginning. We're assigning some metadata, we're using that, and we're uploading everything back up to Shotgun. So when we run this whole network, basically, this is more or less a live view of what you would get in Shotgun. All these assets coming in, being attached to the correct pieces of data, assigning the turntables, and so on. So earlier, Kristen talked about like pipeline possibilities. And so you can see how the low-level tool set that you get with Houdini couples very nicely with these high-level tools you get from USD and Solaris to create something like a full pipeline. And just an interesting side note with where we've made some improvements with PDG is you can see in Houdini 17.5 how sort of slowly the work items come in if you look at that bottom node on the left. And essentially the reason for that is when you had very fast jobs, so something that maybe only takes a couple of seconds to cook, there's actually a pretty high cost of loading Houdini, cooking that thing for a couple of seconds, and then closing that session of Houdini down. And so with Houdini 18, we've moved to this idea of batching work items in an intelligent way. So now, a session of Houdini will stay open and cook many, many work items. And you can see how much faster this second row is than the first. And then on the far right, we even have something called a processor service. And you can imagine that essentially as a session that's open and waiting for commands to be sent to it. So you don't even have the cost of opening the Houdini. It just waits and receives commands and cooks the results. So many ways to approach it and get these faster overall results. But of course, as much as we love Karma and we support Karma, there's the reality is that in productions, people have their own renderers. They have pipelines that exist. They have tools that exist. They want to use those tools, hopefully inside of Solaris. So we have this sort of nice range of third parties who are working to get these render delegates working inside of Solaris. So of course, RenderMan, is very, very nicely integrated. They're very close to the USD team, obviously, and so their integration is very tight. You can see that they can create instances just like we were talking about. They have their own custom UI that sits on top of the standard Houdini UI. They can tie directly into the same light mixer I showed earlier. So these tools are generic, right? Because we use the standard USD lights, the standard USD cameras, any Hydra delegate can then just pick those things up directly. They don't have to re-implement their own lights and their own light handles and so on. And so you can see here with RenderMan how nice and tight that coupling can actually be. But there's more. Here's a render delegate that Arnold is working on. And again, you can see that they're manipulating the same lights that I was manipulating with Karma. They get the same handle. So it creates this unified context that everybody can work in. So the UI stays consistent, the way you work stays consistent, and you can then plug in whichever your preferred renderer is. And you can also see on the top right how there now shows up this Arnold tab on the light, but right next to it is Karma. So any renderer that you have would sort of show up in these lists. So you can add this Arnold-specific parameters to the light node that show up when you're using Arnold. There's also the display options. So these are Arnold-specific display options for how the viewport is currently rendering. And when you've switched to a different renderer, the display options switch to that renderer's display options. So again, it's not just about using the underlying USD technology. It's also making sure that our interface is open enough that these other third parties can plug into what's available and create this consistent workflow. ProRender from Radeon, again, already working in the viewport. You can see this interactive lighting. Things work as they sort of tumble around. So third parties at various states of integration, but all working toward the same goal of having these Hydra heads, again, based on the idea that USD allows you to push the same data to multiple render targets. And then Redshift. And again, Redshift getting a really nice integration. You can see here, again, the live updating in the viewport. You can see they're using all the standard nodes that we've already used throughout some of these demos. And a really nice example is that they're also using VOP networks to author their shaders. So you can work in a very familiar way. You can use the same nodes you would expect. Here, just assigning a triplanar projection. They add some displacement to the ground in just a moment. But nevertheless, the point being, you can see that they have this really nice version of their shader that operates inside Solaris. Here we go. So, all the stuff that we've done, all the work that we've done is hopefully good, and, we certainly stand by, and we hope that it's going to be popular out there in the community. But the reality is when you build something like this, a new piece of technology like this, what you really need is for people to start using it, right? You need to get feedback from people, because a lot of this is not exactly guesswork, but it is sort of throwing a dart and trying to hit a target that's maybe moving on the horizon. So what's really useful is to have people, in the industry who are actually trying the software, trying to work on it. And we were very lucky to have some industry folks from Blue Sky actually sort of get on board and help us testing and using Solaris. So I would like to welcome to the stage Chris Dolch from Blue Sky Studios, who's going to talk a little bit about how they've integrated some of the tools of Solaris into their production. So please give him a hand. Thank you.
Thanks, Scott. Also, I think we need to give a hand to Scott. I think we should watch him use the stage manager a little bit more and all those cool tools. I like watching Scott work. So I'm Chris, and we're really excited to be a part of this this event. Solaris, it really is a game changer. I can't tell you how excited I am. All right, so about 2 years ago, we started investigating how we could make our pipeline better, how we could make it more collaborative, how we could be more agile, all of the things that we want to see in a pipeline. We want instant rendering, all of the dreams that'll come eventually. But we knew that USD was going to be a key part of this because it really facilitates scaling, working together, layerability, as we saw in some of those workflows that Scott did. We had a working relationship with side effects. We've been using Houdini, as most studios have been using, in effects and crowds and whatnot. But after some discussions with them and with others, we realized we needed to start looking at Solaris. And we did some test work and pretty quickly realized that this was going to be a game changer. Not only what it could do with USD, but the potential in the future. So we decided to go all in. And you might wonder what that means, all in. When is Blue Sky going to start using this tool? We've been using it for over a year. Solaris has been used for lookdev and lighting on all of our projects coming after Spies in Disguise. Unfortunately, that means we can't show you the cool work. I know. Tease, tease, tease. But what we can show you are some of the workflows that we've got. Another piece of technology that was talked about at SIGGRAPH, if anybody caught those talks, is Conduit, which is our microservices-based version control, asset management pipeline, and integrates really well with Solaris and USD. And so what we're gonna do is finally be able to show the world some of these workflows. Now in Conduit, a word you're gonna hear thrown around is a product. It's just a version-controlled bunch of files. Generally, it's a USD asset or the elements of a USD asset. And here we're gonna do the hello world that we normally do at Blue Sky, which is with a donut. But since we're in Montreal, we're going to do a bagel. And not just any bagel, but a real bagel, right? So we've got our bagel here, and it looks great, right? The model is awesome. So now we're going to commit that model element to the bagel asset. We're going to revisit this export window, but this is the same tool that every contributor to Conduit uses. And it's PDG powered. So, model looks great. We just finished our training, and now we've been asked to do some lighting. We need to bring in the assets to the lighting work. We've got a wrapper around the reference lop so that we can reference in the USD assets, and this pulls up this product browser, which can be tailored to assets, or in this case, we've got a node for shot work, because everything in Conduit is a product. But the really cool thing, and this is so exciting and really cool, is we've integrated the product browser into the stage manager so that artists who are doing, whether it's asset work or layout or whatever the case may be, if they want to pull in assets this way, they can. So using natural language searching, they can find the assets they want. In this case, we want some lamps and a couple of TVs because we're gonna light these assets. And you can just drag and drop. It references the assets into the scene, and it sets up all the back-end stuff in Conduit to track dependencies and whatnot. Now, I can work on these assets in context of everything, but first I'm going to start by doing them one by one. Hydra is awesome for this because, as we've seen, as Scott's demoed, you can see the lighting as it happens. This being able to kind of do what you need to do, we haven't figured out a good buzzword for that, but we want artists to feel free to do what they need to do. If you're in training but somebody wants you to light a bunch of lamps, go for it. In this case, the TVs needed a texture map. So we can, again, pull in the product browser, find the texture maps, and just drag and drop them into LOPs. And we can see our results live. This was a lot of work internally, but also a lot of support from Side Effects and the RenderMan group too. We'll see a little bit more about that in a second. All right, so our lights look great. Hey, does it look good? Okay, I know, I lit it, so it's yeah, I agree. So since we started so long ago, there really wasn't Hydra rendering support. So we built our own bridge that just translates USD into RenderMan. And with the RenderMan group's help and with Side Effects' help, we can stream deltas from the LOP graph into RenderMan. And in this case, we see them in it, updating live. Now, exporting one part of a model is cool, but we've been working on 9 assets. We can commit all of these at the same time. This is all powered by PDG. That's another piece of technology that Side Effects has been great about supporting, and we are really excited about, because you can do everything that you need to do. No pun intended. We're really excited about Solaris. The future is really bright. Like Kristen and Scott were saying, this tool was originally intended to be a lighting tool, but the pipeline possibilities were out of this world. We had so many artists come up to us and say, I get USD thanks to LOPs, because I can fiddle around with it, and as Kristen said, it's very faithful. I get what that means when you talk about referencing and sublayering. So it's a cool piece of technology. And one last thing, the other reason, apart from the tool that we went all in, really was Side Effects. If you haven't experienced yourself or seen somebody else experience the first time of seeing their bug fixed the next day, when you see that, you'll understand why we are all in with Side Effects. It's an amazing group of people to work with, and we are looking forward to that partnership as it continues to grow in the future. Thank you.
All right, thank you very much, Chris. It's really wonderful and a privilege to have you with us tonight to launch Solaris. You can tell that the scope of this project is massive. And I think we've just scratched the surface tonight with what you can do. And this is all new technology for us. USD itself, Hydra, is new technology. We worked really well with the Pixar USD team and Hydra team, and we constantly evolve the API and our own understanding of how things should be done. And from here on, we rely a lot on you guys to give this a try and help us, take it to the next level really, really quickly. There's a lot of functionality in there already, whether you're doing pipelines like Blue Sky or you're a single person lighting a scene. You see how quickly you can just import a scene from Houdini and then use the tools that we've built for artists, right? These are tools for artists, not just for TD. So all that is there, but all of it needs to evolve. It is fresh technology. It needs you in your hands and your brains and your talents. So please work with us so we can fix those bugs overnight. Is that what you said, Chris? We'll try. All right, so that concludes the first part of our presentation tonight. Maybe the one last thing I want to say about Solaris, which isn't really about Solaris, is all that physically based layout that you saw, which is pretty cool. It's fun, but actually useful. It's both. It's amazing how quick it is. It's exactly the way Scott described it. So that's leveraging all this sort of physics technology that we've been accumulating and polishing, refining over the years. And there it sits, and we've been using it for dynamics, for DOPS. And now here it is in LOPS. But truth is, it could be used a lot more in the rest of Houdini. So I think what you're seeing now with LOPS and layout is what you'll be seeing more and more in Houdini. So we have this plan, this intent to leverage that technology throughout Houdini, and you can easily think of ways to use that for modeling and for character, full body IK with fancy physics attached to it, and so on. So this is a path that we're on that doesn't stop with Solaris. It should permeate the entire Houdini landscape. All right, so we have part 2 because we did a few more things. It wasn't just Solaris. We've been having a lot of fun with Solaris with lots of our R&D, but we like to innovate on a number of fronts, and in fact, we have to innovate on a number of fronts. I should say very clearly, too, that as we look at areas like this, which go beyond your typical visual effects, the things that you expect from side effects, we are very keenly aware that our VFX has to stay strong and move fast. That remains the key, fundamental, essential ingredient of what Houdini is and what you, as our community, expect from us. So the second part of the presentation will be about that, and lots of that, in fact, and also about geometry and the tools there, because that's another interesting realm. We know we've been using and developing SOPs since the beginning of Houdini, and that whole list of SOPs has grown, and we have some new ones that are architected in the best of ways for this age, and some that have been left behind. And so we are now very focused on making sure that we sweep through all our technology that has to do with geometry and bring it into sort of this new age. And hopefully to that we're adding not just parity and functionality, we're adding a lot more functionality, but we're also adding a lot more ease of use. Okay, Scott, back to you.
Okay,
Thank you.
Thank you very much. Okay, so we're going to start out with modeling, and we're kind of using modeling as a catch-all tool for sort of geometry modification. But let's just dive in and take a look at some of the updates. So first of all, we've had this bend tool around for a long time. It's very powerful, but it was very complicated to use. Nobody understood any of the handles. It was sort of a mess. So as a good sort of starting point, we start thinking about this sort of new, better forms of interacting with things in Houdini. We immediately said this is a good testing ground because it's a complicated node. How can we present handles to people that make sense? And so this is sort of a testing ground for where we can hopefully go with a lot of these tools. And so here you can see, hopefully, the handles that make sense. You can intuitively look at them and sort of understand what's supposed to be happening with these things. When you grab them and move them, they make sense. They do the things you would expect them to do. And bend has a lot of capabilities. There's this squash and stretch capability. There's the twist. There's the bend. There's stretching. So there's a lot of elements here that this node is controlling. And we want to keep you close to the viewport as possible. Like, parameters are absolutely useful, especially for things like ramps and so on, but it's just necessary for an artist that they feel comfortable working directly in the viewport as much as possible, especially when you talk about modeling tasks like this. So here we're really trying to push this and say, like, yes, we want you to feel comfortable here. We want you to feel like this is a tool that you would use in a practical way. So here's just another example where we're also using hotkeys. We're trying to use more and more hotkeys to let you do things like change the capture axis automatically, hide handles that you don't want interfering with what you're doing, allowing hotkeys to do things like snap things to different values. So, when we modify these things, you get expected results. Hold down control to snap to 45-degree increments and so on. And so again, really just trying to make the tool feel like what you would expect it to feel like. It does the things you think it should do. And along that way, we're also coming at it from the other side, saying, like, we need to improve some of the underlying technology. So here's an example of our update to the bevel tool. So a big problem with beveling in in any sense is things like intersecting geometry, overlapping bevels. It's a real problem. Beveling seems like a simple concept, but is actually extremely complicated. So what we've done is really taken a hard look at how we can maintain the topology. So this isn't sort of a Boolean bevel. This is something that is used for, box modeling, quad topology. So we want to protect your topology as much as possible. And here you can see on the left, we have this blue line indicating, an edge that's been cut into this geometry. And it's not parallel with anything. But the bottom edge of the bevel is able to accommodate that edge and continue to bevel. And on the right side, you can see that the top loop, if you imagine a bevel being two-sided, has nowhere else to go. It stops at the middle of the geometry. There's nowhere left to bevel. But we're actually allowing the lower loop to continue if there's room left there. So you can actually move as far as you can possibly move, basically. We want to give you as much access to all the space on the geometry that's available. Of course, this is controllable. So on the left, you can see that we're stopping the loop. So when they collide with each other, if you want a perfectly uniform bevel all over your geometry, you want to stop all of the beveling at the same time. However, on the right, we're saying, if you're a loop that has room to continue beveling, just go ahead and do that. And these types of complicated topological actions are difficult to deal with, and so they require this sort of hardcore re-architecting of the underlying tool, which is what happened here. This is basically a complete rewrite of our polybevel. And then in a more practical scenario, we've also changed things like how we deal with connected edges, so we can filter out pieces of geometry that are getting in your way. We can also deal with profiles a lot better. And again, keeping the same idea of colliding so that you can extend that all the way to the end of the geometry. We can also now change convexity. And just as a nice little side note here, we've also added hotkeys to our radial menus. So if you want to assign a key to bevel, instead of motioning to get there, you can basically hit, CB, CD, whatever chain of actions you want to get to that point. But like I said previously, we're doing indirect handles so that you can create these bevels without having to change parameters directly. And overall, just trying to make things, again, move and act in the way you would expect them to. And if there's capabilities there that let you do fancier things like this collision detection, that's great. But it really should just feel good to use it. And then, of course, custom profiles. So here, just a view showing how we're using a ramp to change the bevel profile. So you can really dial in the look that you want exactly. So, sorry, I skipped ahead there by accident. Sorry about that. So here now, just combining a couple of the tools together. So a bend to sort of create this tight spiral of geometry. We can offset that so we can create like a spiral like this, and then of course a bevel on those edges. So just trying to bring all the tools together, make things work together in a nice way, let you model the things you want to model. So here's an example of the new sweep node. So sweep is sort of the backbone, no pun intended, of a lot of procedural geometry generation. And it was very, very powerful, but you had to do a lot of workarounds to solve very common problems. For instance, UVs, or matching geometry when it folds back in on itself. So the new sweeps up handles UVs automatically. It computes them in all sorts of ways so that you can get no seams along the U or the V boundaries. Even if the geometry loops back on itself, we'll line up those seams for you automatically. We can also generate different types of geometry. So sweep by default now creates geometry directly. So you can see we have essentially a tube geometry, kind of a ribbon geometry, something we're just calling a square tube. And then of course custom profiles that you can feed in. And you can feed in multiple profiles at once. And at the bottom, we're just showing that we can twist this geometry and guarantee that on a closed curve, the geometry will match up with itself, and we'll distribute the amount of twists back around the curve so things line up properly. And you can sweep multiple curves at once. You can use ramps to control the scale. Of course, attributes exist for all these things, so you can use attributes to drive up vectors, tangents, pretty much everything that you would want. And here we're just animating these three profile curves using p-scale. And again, you can see in this case the UVs expanding and stretching, but you could do it in any number of ways depending on what your needs are for the UVs on your geometry. But it's not just capability, it's also speed. So on the top, we have the old sweep SOP, and on the bottom, we have the new one. And so you can see that even though we're creating UVs, we're doing extra work in the Houdini 18 version. And this is just creating thousands of curves and sweeping a circle along them, essentially. You can see that Houdini 18 vastly outpaces Houdini 17.5. It starts out about 16 times faster than the old sweep, and by the time it gets to the end of this huge array of curves, it's something like 30 times faster. So it actually scales very well. So it means that you can handle huge amounts of geometry much faster and get the results that you want out of a single node instead of doing for each loops to get every curve to sweep across, doing things to cut up your UVs and stitch them back together. It really just takes a lot of very common work and puts it directly into a single node. And then there's direct modeling. I want to just push points around. And some of these, in some ways seem like, well, of course you need this. And it's true. It's taken us maybe too long to do some of these things, but we're finally getting around to them. So you can, for instance, grab edges, slide them on the geometry, blend them into the surrounding edges. Very typical sort of standard modeling tools that are just really a base requirement if someone's going to work interactively and build things. So we've made sure to try and support those. Also things like the new point weld SOP. And this is a really good example of that idea of UI that I was talking about earlier, how we want to make things clearer to you, to make things obvious what's happening here. And you can see this is just like a drag and click operation, and this sort of little circle showing you what you're snapping to, what's going to get fused together, an interactive fuse, essentially. And it actually underlying uses the same idea as the fuse SOP, just with this interactive state on top of it. And then one of our developers made this example showing how these points can also be averaged together. So you see as we select two, there's an average point in the middle. So we're taking these sort of opposing things and we're finding a middle ground and bringing them together. Our developers are very poetic when they create these examples. And here we're actually doing something kind of interesting, which is almost the opposite of what I just described, which is taking something that we've had for quite a long time as an interactive mode, which is a growing and shrinking of a selection, and then putting it into a node itself. So this now becomes a procedural operation. So basically, the group expand node can take a seed polygon, a seed group of any kind, and then expand it using a step size. And so you can see as we change the steps, the selection grows. And where this starts to get interesting is we start thinking of collision obstacles. So we can create a group of things that it cannot expand into, and it will sort of grow along the surface and grow around those collision primitives. And then even further, we can say, well, let's use some attributes to determine this. So in this case, we can say, well, you're only allowed to grow into polygons that are at least 4 degrees off from your seed polygon. So you can see we can create these really interesting growth patterns just by using this normal restriction mode. And then because a lot of this information can be used in very powerful ways, we also encode the steps into a step attribute. So the number of steps is recorded in the geometry as it expands. Here we're just visualizing it using these simple colors. But here's sort of a slightly more practical example, if you can call deforming a squab practical. But you can see on the left the group expanding, and on the right we're basically feeding that step attribute into more or less just a poly extrude and a color node. But we get this really nice option that you could certainly have done with maybe a solver or something like that. But again, we're just putting a very simple tool in the hands of artists and letting them do cool things with it. Here's another one, a very long time requested feature. First of all, we're just going to make a pattern here. We're going to select a bunch of polygons along this curve, and then we're going to use a local space edit. And that just means that each one of these sort of islands of selections more or less use the same transformation, but in their own local space. So this is a long time request from modelers. It's basically a critical function if you're going to do serious modeling, and we finally have implemented it in the edit SOP, and you can see you can get really nice, consistent results even along this overall curving geometry. Perhaps more practically here, we've sort of selected the inside of these pieces of this car wheel. Earlier today I called them car holes because I don't know anything about cars. So here we're modifying the car holes at different rates using this local editing. But you can see immediately why this is useful. You can do many operations at once instead of having to break it up into multiple steps. And then terrain, terrain essentially a type of modeling. And we've had this node called the height field terrace. And it's great. It would build these sort of steps into your geometry. It's something that's really necessary for modeling terrains. The problem is it was very even, almost mathematical looking. You would see this very obvious sort of clean steps through your geometry. So the new height field terrace node allows you to break that up, add randomness, use ramps to say where these things are occurring, and you can get much more natural results like this, where you don't have this completely uniform step size across your whole geometry. It just breaks things up, allows you to create much more natural looking effects. So a while back, we created a sort of a group of TDs, and they created something called the game dev toolset. And the idea here was that we could have this group of people dedicated to creating tools to solve specific problems of game dev people. And it was great. And the idea is that they can act very quickly, very rapidly. They can target very specific needs. And it has been really awesome and really successful. But what we've found is that over time, the idea that game development tools are somehow extremely different from standard 3D animation or filmmaking tools is sort of falling apart. Those worlds are getting closer together in a lot of ways. And so what we've decided to do is partially just to let people know that if you're not a game developer, these are still useful tools. Like, look at these tools, use these tools. And it's already happening. So to make that a little clearer to the community, we've just created this idea of side effects labs. And that just expands the types of tools that they'll be using. They still have the same mandate, a small group of TDs dedicated to making these fast tools, iterating on them quickly, and they can be separate from full releases. They don't have to be tied to sort of the baggage of a full release, like making sure everything is backwards compatible and so on. So Side Effects Labs, essentially the same concept as it was before, but opened up so people can understand better that, no, you should try these tools, like try these out in any workflow you have. It's not just game development. And you'll find a lot of really super useful tools in there. And just to sort of drive that home, here's one of the new tools, which is an update to our Substance Designer plugin. And you can see it's been implemented essentially as a compositing node in COPS. All of the parameters from the substance have been promoted, and you can use them in a standard compositing workflow to generate texture maps, in this case on this torus. So you can see just using, we can point to those COP networks. We can call out the different planes for diffuse and roughness and so on, and have those apply to the shader there in the viewport and showing the real-time displacement as well. So then let's take a look at sort of a pipeline that sort of uses a whole bunch of these tools. So here is Luis, one of the TDs that I'm talking about, working for Game Dev, getting scanned. He looks super excited about it. So basically a photogrammetry idea where we're scanning a person and we need to take that a very dense point cloud of data, take all those images, and we need to process them in some way. So all of these steps here use different plugins, different pieces that have been created for Side Effects Labs, previously the Game Dev toolset. And you can see a bunch of products being used together with Houdini, using base Houdini technology alongside these plugins, alongside these Houdini Lab specifically designed tools to go all the way from a high-res scan to a sort of a game-ready, low-res texture-mapped asset. So now we're going to move on to essentially effects. And obviously, as Kristen said earlier, effects is always a focus for us, even when we have other things. Effects is important. We always work on it to some degree. And despite the fact that Solaris is a huge project, we've actually made some really huge changes to our simulation tools for Houdini 18. So first of all, we have an adaptive pressure solve for our flip solver. And what that means, practically speaking, is that you can, in certain circumstances, cut your render times in half. It's really kind of amazing how well this works. And essentially it was because this pressure solve dominated the overall simulation. So by making it adaptive, you really cut a lot of the overall processing time down. And just to be clear about what we mean by adaptive, you can see in this sort of visualization at the bottom that near the surface, where obviously the detail is very important, we have these small detailed areas in the pressure solve, and in these deeper areas where maybe things aren't as important, don't have much effect on the overall look, we use these larger sizes, meaning we have to do less work. And it's also important to note that this works with narrowband, so you're really combining these technologies together to have a smaller overall amount, and then even within the smaller overall amount of processing to work adaptively. So you can see there's some improvement in Houdini 18 even without the adaptive pressure solve, but then a real jump when we enable the adaptive pressure. What's also really interesting to see here is that despite the fact that we're solving essentially much less of the overall data, the look is extremely consistent. Like there are very likely differences in these simulations, but they're not in any way bothersome or even noticeable in this particular case. And even if we sort of zoom in and take a close look at one of these simulations done by Igor Zanish, who's done a lot of testing for us over the years, you can see that, this looks great. There's no indication that we're somehow losing any data. So the adaptive pressure solve is a huge win for anybody doing these kind of simulations. And Vellum, I think it was about a year ago that Vellum was released with Houdini 17, and it's been great. There's been huge adoption. People are jumping on it. It's used for all kinds of really interesting effects, and the fact that it's XPBD based means that it's useful for all sorts of crazy things that you wouldn't think of a cloth solver necessarily doing. Having said all that, when we created it, the focus really was a cloth solver. We wanted to make sure we could do cloth. We wanted this for character effects, and we've continued to push that side of things. So here's just an example of two characters. They're moving quickly. They have these sort of silky clothes on. Just to point out, where Vellum currently is, things are looking pretty nice. But with a lot of character effects, a lot of times it really comes down to having control over exactly how things look, because characters have a lot of focus on them, and we're used to looking at things like clothing. So a really nice set of tools that we've created for Houdini 18 basically all revolve around velocity and how velocity is transferred to the simulation. So on the left, there's sort of the unconstrained simulation, and the simulation works fine, but you can see that because the actions of the character are so dynamic, he's moving so quickly, that sometimes the cloth whips around in ways that, even though it might be physically correct, is sort of distracting to look at. And on the right, we can use these new velocity blending tools to say, well, okay, I want to actually pull back some of that velocity. And it isn't just about scaling the velocity down, it's about matching the simulation's movement to the underlying movement. So you can see that even though we're getting the correct motion, like it doesn't look like it's like underwater or it has a lot of drag on it, it's much calmer. It seems much more subdued. And so you have a lot of control now over how much of a simulation, how dynamic a simulation is going to be. Along the lines of these character tools, something that's really useful is to be able to run a lower res simulation and sort of have some idea that the higher res simulation will match, right? If you're going to spend the extra time, hopefully your setup will work across. So we put a lot of work into making things sort of topologically invariant so that you get a very similar look of a low res sim to a high res sim. Obviously, there's going to be more detail in the high res simulation, but you should more or less get the same overall motion, assuming you have enough substeps to do so. We also have sort of an FEM-like tetrahedral constraint with volume preservation to some degree and plasticity. So you can see here that we can take this dough and sort of flatten it out. And even though this is a mesh, this isn't like a fluid simulation, you're able to get this sort of completely flattened out piece of geometry holding its shape. And then something called a sliding constraint. And this is a really interesting new type of constraint that basically allows you to constrain a point to another piece of geometry, but have that point freely move across the surface of that geometry. So here we're visualizing the constraints as these sort of dots with lines connecting them. But essentially, this object is free to slide back and forth across this wire. And of course, because it's always useful to have, you can also put attributes either on the constraint side or the object being constrained. In this case, the blue, he slides faster, and on the red, essentially has more friction, so it slows him down. But it isn't just single threads. You can actually just have him dynamically move across the geometry that's sort of any shape. And so there's no animation here. This object is just sliding along. You can see his legs sort of dancing along the web as he just finds areas to slide along. And it's nice to know that this is also a two-way interaction. You can see the weight of the spider is pulling on the web, right? This isn't a baked-out simulation. But it goes further than that. It's not just wires. We can transition from wires onto the surface of cloth and then back onto wires to get a really nice dynamic look. And it's really kind of amazing how much character you get out of something that looks like it's desperately holding on to something. But it's, again, really powerful that it can do this. This isn't a constraint of one type. It can slide and move across different surfaces. So let's just take a quick look of how you set this up. So essentially, we're here in SOPs. Stop playing. Click. There we go. Yes, sorry. Here we are in SOPs, and we're just doing a standard attached to geometry constraint. And we're just going to select the sort of bottom of the spider's legs. And when we run this simulation, you can see that it does what you would expect. It attaches the character to the surface, but there's no sliding. And basically, what's great is that the sliding constraint more or less comes down to just enabling sliding. So you enable sliding, and more or less you're setting the amount of friction for the slide. And you can see our spider now, he goes around to the bottom side of the torus. And of course, the spider himself has a tetrahedral mesh inside of him. So it's two types of simulations. And now decreasing this, you can see we get a nice sort of Tarzan effect as our spider makes his way across the center of the torus. And that's actually really interesting to note, because what you might expect is that these constraints would sort of jump across gaps, right? Just finding the closest surface or something like that. But we're able to constrain them to the actual surface of the geometry. So the objects sort of move around the discontinuity. And here, combining those two concepts now with the left being sort of faster and the right being slower. And of course, the green lines are just indicating where the constraints are. They're not actually part of the simulation. And then, like a lot of other constraints, they are dynamic. So if we drop these frogs on this cube, which is a very common thing to do, they sort of cling to the cube to survive this calamity, this frog calamity. But the point being that these constraints can be created dynamically. They can break, they can do all the things you expect Vellum constraints to do, while also having this nice property of sliding along the surface. So all this stuff is great, and Vellum is awesome. It's fast, it's stable, it's really good. But when you want something that's supposed to be 100% physically believable, FEM is sort of the king of that realm. And there's a cost to it. FEM can definitely, it takes a toll when you run a simulation like this. But we actually have put a lot of effort into making the FEM solver faster and more stable in Houdini 18. So it's quite a bit faster, as a matter of fact, as well as implementing some new models, like this Neo-Hookean model that has a bunch of advantages, but one of the key ones is this better volume preservation. So you can see that as we compress these gummy bears in this tube, that they actually do sort of fill in all the available space without becoming flattened out in an unnatural way. It feels like an actual object under pressure. And here in the render, I think it gives even a better idea in some ways of just how nicely and tightly packed they are, and yet how stable the overall simulation is. And related to that idea is, again, using something for flesh like this. So here we have an elephant seal. I believe the technical term is galumphing. He's galumphing along the beach here. And you can see that we're preserving the fleshiness of the character while also having this dynamic wrinkling occurring on the surface. And something that's really interesting is that the underlying animation here is actually extremely simple. It's just coming from these basic, you could think of them as bones, I guess, that are just inside the mesh, the FEM, the tets are sort of softly constrained to them, and so you get a lot of this really interesting dynamic motion without actually doing a lot of work under the hood. It's some very simple animation. That's the nice thing about how physically plausible FEM is that even when you do sort of simple things, it looks very believable. Another really nice advantage of FEM is that it is very much independent of resolution. So you can do a very low res iteration. You can see here 3 frames per second on this low res mesh and actually get very similar results to the high res. Obviously the high res mesh has more detail and so on, but you actually do get a very surprisingly close match between them when you do. So you can iterate on low res meshes, get all your issues sort of worked out before you do your costly high res tet mesh. And then FEM is also capable of basically having a skin on the outside of its geometry. And that can have its own properties. So the inside of the creature, the elephant seal here, can be quite sort of gelatinous, whereas you could have very thick skin on the outside. So here are just some wedges about how stiff the skin is, and you can kind of see how much effect that has on the overall wrinkliness of the surface. And here again, just a render with the 4 times stiffness to see the nice, very believable wrinkling and bending on the surface of this character. So destruction, this is obviously a very important set of tools in Houdini. Rigid bodies are very popular. And we've actually put quite a lot of effort into the tools in Houdini 18 to give sort of new ways of working. So first of all is the fracturing side, what you're sending into the simulation. And essentially what we've done is taken our material fracturing workflow that we've created, I think in Houdini 17.5, and added the ability to customize it more, add custom cutters to the geometry so that if you're trying to create something very specific, you can go ahead and do that with your custom geometry. We've also added some tools to help with a very common problem, which is that when you pre-shatter something, which is what you almost always do with simulations like this, is that it shows up in the render. Obviously, glass isn't pre-shattered. You shouldn't see things on the inside of the glass, and it's a real pain to remove that at the correct time. So in Houdini 18, we have some tools to help you do that, to identify those places and only have those interior pieces show up when it actually makes sense, essentially when the overall geometry has broken. And you can see you have some control over that because sometimes glass cracks without actually coming apart. We've also taken a look at chipping. So chipping is just the idea that if you have a big piece of something, it makes sense to be able to add sort of small chunks to the outside that might break off. Now in Houdini 17.5, we had a tool for doing that, but it kind of just created smaller and smaller pieces. In Houdini 18, we're better about actually identifying places where chipping should naturally occur, essentially at the sharp points at the ends of these pieces. And we make these small cuts so that when things break apart, they eventually sort of round out over time the way you would expect something tumbling along a surface. And when you compare it directly, you could see very obviously that the bottom one definitely feels more natural, the results feel more correct. And while the first one is fine in terms of a simulation, the chunks just don't feel like believable. And then on top of that, we can add emission on those points. So here we're actually doing a secondary rigid body simulation, emitting small chunks from those chipped pieces. So this is something that might typically be driven by a particle effect, but we're also enabling here for actual rigid bodies. And one of the most significant changes to the bullet solver and our rigid body solver is that we want, again, to bridge the idea of being an artist working familiar tools at SOPs and these idea of these physical tools. And a way that we've done that is by saying, like, okay, well, let's literally bring them together. And so in this example, I'm just creating a grid, scattering some points on there. I'm using an attribute randomize to create some velocity. And I'm just going to copy a box to those points. Pretty standard stuff. And the big change is that once I've set up my velocity properly, I can just add a rigid body solver here at the SOP level. And so now I can plug directly into SOPs above, hit play, and get an RBD emission directly in SOPs in this very simple network. And this really helps people understand more about what's happening It simplifies their overall workflow. As you can see, a very simple network here, and we've exposed tons of the parameters of the bullet solver to this SOP level solver in order to let people work with it in a very direct way. Of course, if you want to customize things and you want to dive inside, that's all possible. You can still build these tools inside our standard DOP network. But what this lets you do is that for your standard cases, these high-level things where you need to quickly iterate on an idea, you can do it in this very simple way. Now, a really awesome new feature of this solver is something that we're calling guided sims. And so on the left, you can see a piece of animation, and on the right, a simulation driven by that animation. And so something that you might think by looking at this is that there's some direct relationship between these two things, that one is sort of derived from the other. But that's actually not at all the case. The geometries don't have to have really anything to do with each other at all, apart from their proximity. So here's just an example. Again, we're just going to do a standard sort of Voronoi shatter on this pillar. I'm going to throw down a RBD solver and turn on a ground plane, and then hit play. So right away, we've got a nice action there. There's no constraints. There's nothing holding this together. And now on this second chain, I'm going to just create a small box. I'm just going to copy it a bunch of times. And really the point here is just to show you that there's no relationship. We haven't made geometry from the original geometry. The animation is happening on an arbitrary piece of geometry. And then we're just going to use our new bend tool to add some animation to our column on this right-hand set of nodes. You get to see my awesome animation here. I'm an excellent animator. Basically, we're just going to bend this back and forth and then bend it a little bit. So now that we have this animation, we can plug that into our RBD SOP, turn on Use Guides, and basically just add a little less of the animation into the overall simulation, and immediately we get this. So like I said, there's no constraints here, right? We're not modifying constraints. We're imparting the animation directly onto the geometry, and there's lots of controls over how tightly it matches the underlying animation. And here you can see again that we're splitting this geometry. So the underlying animation is coming from two pieces of geometry, right? We can just bend them. And this speaks a lot to what Kristen was saying earlier, that what we're trying to do is take these tools that exist, that artists are used to, maybe even animators are used to, people who would bend something like this as a preview for what they want to happen. And then usually it's the effects artist's job to kind of go in there and say, like, okay, how do I get this to match? How do I match what the animator was trying to do? And in this case, we're pushing those worlds closer and closer together. So what the animator is doing, the results that they want, can directly influence the physical simulation down the road. And again, we want to push these closer and closer together, merge these worlds so that people can work in the same way to get these different results. Another interesting idea here is that, of course, we can use one simulation now to drive a rigid body simulation. So on the left is just like a very simple FEM box dropping on the ground. It wiggles and it does all the cool volume preservation you would expect. And on the right, we're adding those properties essentially into this rigid body simulation. So you can see these things sort of bouncing and jiggling and almost look like they are bending, even though obviously they are not. They are, as the name suggests, rigid. And you can immediately start thinking now of more interesting things, right? Now we can do these big, complicated scenes that are very difficult to art direct. When you have something very complex like this, it's hard to iterate because you're never exactly sure what's going to happen to the underlying simulation. In this case, we're just using, I believe, 2 twist nodes to sort of push these buildings together. But they can become more layered than that. So here's a really awesome example of this building. It's high detail. I don't even know how many pieces are here, but there are a lot of pieces. And you can imagine getting the timing right, getting all these pieces to work together in exactly the way you want is very difficult, especially with however long this simulation takes. I actually have no idea how long it took to simulate this. But what's actually happening here is underlying this simulation is actually a very low-res, essentially Voronoi fractured version of this building. And that you can iterate on extremely quickly. You can run that in literally probably real time. But you can work out the timing, the positioning of all the pieces. All those things can be worked out using a low-res sim in advance. You could even take the results of that low-res sim and use some of the modifiers that we've talked about today to bend and shape those over time, and then feed them into this very complex simulation where you can be sure now that you're at least going to match the timing and the overall motion, except you're going to add massive amounts of detail on top of it. And pyro. So, rigid bodies are important, and even in that last example, you could see that, there's some dust in there. Pyro, smoke, those are important features for effects. They're often integrated into other effects. So for Houdini 18, we basically wrote a completely new solver. I mean, there's parts of it that are reused, but this is a sparse pyro solver, with the idea being that you want to do your solve only in the active parts of your simulation. So if you imagine that we have something moving through space like this, a lot of the overall container that it would be in is essentially empty. And so what the sparse solver allows you to do is basically simulate in the areas where the effort is going to be put to best use. So I think maybe a slightly better visualization of this is actually to show you what this simulation looks like from an outside camera. So the overall container, as you see, is pretty standard stuff you would expect from a pyro sim, but these small blocks that you see inside are the actual active regions that are being simulated. And you look in the bottom left, you can see that over time, we actually use less and less of the overall container, right? By the end, I think we're only down to 7%. So it makes sense to try and constrain your simulation to just that active region. And to do so, we needed to create a sparse version of our standard pyro solver. So this is now the standard solver in Houdini for doing pyro simulations. We've also put a lot of work in to simplify the overall process. So here's an example. Again, we're just going to do a very quick workflow example. We're going to start with a rigid body simulation, probably the simplest rigid body simulation you can do. We're just going to add some velocity to a sphere and sort of shoot it up into the air. Excuse me. So now we've got this bouncing ball. Let's stay in SOPs, and we'll start using some of our pyro tools to build a source out of this object. So you can see right away the benefit of having a rigid body solver in SOPs is that you can go directly into other tools. And that actually means the pyro solver itself has also been promoted to a SOP level tool. So I can plug this into this bottom node, the pyro solver, and now I immediately have a rigid body simulation feeding directly into a pyro simulation, all in one context, all at one level, everything in one place. And so now when you want to tweak, the input and the output of these things, it's all there for you. And you can see, again, because it's sparse, you get a nice advantage to these sort of simulations that travel through space in these configurations that would actually be quite expensive if it was not a sparse solve. And to go along with that, we've updated all of our shelf tools as well to use this new sparse pyro solver. So just trying to make sure you have examples to work from. But a nice sort of benefit to this new workflow is that we've also made the shader much more tightly integrated. So this is just the viewport we're looking at. These are flipbooks. These are not renders. So what we've done is taken the shader values that you set up in the pyro solver, and we've basically made them match as closely as possible to the pyro shader for render time. And so the values you set there can transfer over directly. So it removes some of that barrier where you would make settings that look nice in the viewport, and then when you went to render it, you had to struggle to get things to match. Now, because we've tied those two worlds together to some degree, especially with the SOP version, any tweaks you make to the visualization in the viewport transfer over to the pyro shader. And so these are just the standard new tools. We've got a nice little explosion. And then an interesting one that uses a new node called pyro source spread, which allows you to take an object and spread essentially fuel along the surface of that object. So here we kind of start with some really hot area in Craig's sort of butt, and then, which seems natural, and then the fire spreads from there and covers the entire object. Again, there's a shelf tool to do this. It's a nice way of getting in and seeing how some of these new setups work. So again, because it's sparse, you get some really interesting advantage. You can see that about a third of the time, which is nice, about a quarter of the memory. But the interesting thing is that even though it's faster and less memory, it's actually quite a few more voxels. So you get more or less for more for less, whichever way that goes. You can figure it out later. The point is it's faster. So now let's take a look at something that you might not think necessarily is that useful for a sparse solver, but you still get a huge advantage in time, this massive forest scene, which you absolutely could have done with the old pyro solver, but there would have been a huge cost to it. And there's still a pretty large cost. It's a very high-res, very large-scale scene, but now you get the advantage of much less memory, faster overall time, but potentially actually more detail than you would have got before. So it's sort of a win all the way around. And so that ends my portion of the presentation. Hopefully you enjoyed our features. I'm going to welcome Kristen back to sort of wrap up, but thank you very much for your attention.
Thank you, Scott. Is this all you got?
That's it.
Yeah, we'll try to cover a lot of ground in this release, and as we always do. In fact, the full feature set, or the high-level feature set, is coming up. It's a long scroll. Hopefully, each and every one of you will find one or two things of use in Houdini 18. We hope to have gotten you excited about Solaris and these other things. We hope to see you again soon. We try to release every couple of months, and not too fast, but also not too slowly. And as always, there are things that are not on the list. That's because no release can touch upon absolutely everything. But rest assured, we have a good sense of what the list is that we want to tackle next. And in fact, we have a couple of things in the hopper right now, including something that is potentially quite disruptive to do with character. But that's not for this release. We'll talk about that a bit later. All right, and before we end, I would like to thank everyone who's, first the release date, late 2019, so very, very soon. We still have to touch up a few things and write some docs, goodness, and lots of tutorials and all those good things, but it's very close and it's looking very good. So I'd like to thank now everyone at Side Effects who's helped make this release possible. All the developers, of course, all our TDs, our interns who are fabulous, even though we have them just for 4 months at a time. And our testers, our QA and docs team, a small team, but really valiant. And our alpha and beta testers, always, you're fantastic. And please contribute more to alpha and beta. As the scope of the software grows, we need more people, VFXers, modelers, lighters, renderers, whatever fancies you, contact us, knock on our doors, take the door down if you need to, and get in. We need your help. And finally, thank you to all for using Houdini and for being here with us. Enjoy Houdini 18 and see you soon. Good night.